Hello friends, this is basically a crash course of physics JEE syllabus. We have subdivided the physics syllabus into the subtopics. Okay, so the first topic which we are going to begin off with is kinematics. Now let me first discuss the few formulas which are in this topic. Okay, so my first topic is kinematics. Okay, now let us begin off with few formulas. The first formula being average velocity vector and acceleration vector of a point. Okay, so average vectors of velocity and acceleration. The average velocity vector can be represented as this. Okay, it is given by delta r upon delta t. Okay, where delta r is the small change in the displacement vector, delta r, it is the small change in displacement vector, and delta t is the small change in time. Okay, and the average acceleration can be represented by this, is going to be equal to delta v upon delta t. Okay, where delta v, it is the small change in velocity vector, and delta t is the small change in time. Okay, now let us move on to the instantaneous velocity and instantaneous acceleration. Instantaneous velocity it is defined as the time rate of change of the displacement vector. Mathematically it is written as dr upon dt. Okay, so it is the rate of change of displacement vector with respect to time. Okay, so this is my instantaneous velocity. Okay, let us now move on to instantaneous acceleration. Instantaneous acceleration is defined as the rate of change of the velocity vector. Okay, so it is given by dv upon dt. Okay, fine. Now let us talk about the case when a body is rotating in a circular path. Okay, so if a body is rotating in a circular path, it will have basically two accelerations. Okay, so let's say the body is rotating in a circular path like this. The radius of the circle is r. Okay, and at any instance of time, let's say the particle is at this point, it has a velocity, let's say v. Okay, now at this particular point the body is going to have two accelerations. One acceleration would be the tangential acceleration, which would have the direction same as that of the velocity vector, and the second acceleration would be the normal acceleration, which would be radially inwards towards the center. Okay, fine. So this body is going to have two accelerations. One would be at, which will have the same direction as that of the velocity vector, and an, which is the normal acceleration. Okay, which is going to be directed towards the center. Okay, fine. So this is given by an. Now at That is, the tangential acceleration is going to be nothing else but dv by dt. That is the rate of change of the velocity vector. Okay, and the normal acceleration is given by v square by r. Okay, this can also be written as omega square into r, where omega is the angular velocity of the body at this instance of time, where omega and v are related by the formula omega equals v by r. Okay, at this particular instance of time. Fine. Okay, now let us talk about the distance which a body covers. Okay, distance covered by a point. Fine. So distance covered by a point, let's say it is denoted by s. It is given by integral of v dt. Okay, where v is the modulus of velocity vector at any particular point. Okay, where v is the modulus of velocity vector of a point. Okay, now let us talk about the angular velocity and angular acceleration of a body. Fine. Angular velocity of a body is given by the rate of change of the angular displacement. Okay, it is similar to velocity, where velocity was defined as the rate of change of displacement. For angular velocity, we will define angular velocity as the rate of change of the angular displacement. Okay, so angular velocity is defined as d phi by dt. This is basically the instantaneous angular velocity. The average angular velocity would be defined as del phi by del t. Okay, that would be similar to the average velocity. Okay, so where phi is the angular displacement, okay, angular velocity is represented by omega. Okay, now let us talk about angular acceleration. The angular acceleration is defined as the rate of change of the angular velocity. So it is going to be defined by d omega by dt, and it is represented by alpha. Okay, here omega is the angular velocity. Okay, fine. Now let us simply relate the different parameters of a rotating body. Okay, let's say a body is moving in a circular path at any instance of time. Let's say it is at this point. It has got velocity v, it has got angular velocity omega, it has got angular acceleration alpha, and it has got tangential acceleration a. Fine. So let us see how these terms are related. Actually, v and omega can be related because they are similar terms. I mean, they can be related. Okay, so v would be given by omega into r. Okay, Fine. The tangential acceleration is going to be related to the angular acceleration as a equals alpha into r. So this is my second relation. Okay, fine. This is basically my tangential acceleration. The normal acceleration would be given by v square by r or omega square into r. Okay, where I've simply replaced v by omega into r. So I got this expression. Fine. Now let us find out the equation of motions. Okay, I had defined the instantaneous velocity as v I defined the instantaneous acceleration as a was given by dv by dt. Okay, so if I simplify it, this would imply dv equals a into dt. Okay, if I integrate on both the sides, time is going to be from 0 to t, and let's say the body had an initial velocity of u and a final velocity of v. If I integrate this, I'll get v from u to v equals a into t from 0 to t. What I mean to say is that at time t equals 0, the body had the initial velocity of u. At time t equals t, the body has final velocity of v. So if I put in the limits, I'll get the expression like v minus u equals a into t, which gives me the first equation of motion as v equals u plus at. It should be noted that this equation of motion has been derived keeping in mind that the acceleration is of constant magnitude. Okay, had the acceleration been a function of time, I would have to integrate this whole term by keeping a as a function of time. Okay, so in that case the result would have been completely different. Okay, now let us try and solve the second equation of motion. Fine, v is given as ds by dt, right? It is the rate of change of the displacement vector. Okay, so ds can be written as v into dt. Okay, and v I can put it as u plus at. Okay, so if I integrate on both the sides, and let's say at time t equals 0, at time t equals 0, the displacement was 0. At time t equals t, the displacement is s. Okay, fine. So if I put in v as u plus at, okay, so if I put in v as u plus at, I'll get ds from 0 to s equals u plus at dt. Okay, from 0 to t. Okay, so if I put in the limits, I'll get s from 0 to s equals ut plus half at square, where t varies from 0 to t. Okay, so this gives me s as ut plus half at square. Okay, fine. Okay, now let us, from this particular expression, replace t as v minus u by a in this expression. Okay, so in this expression, this is basically my second equation of motion. Okay, in this expression, let us replace t by v minus u by a. So in order to find out the third equation of motion, I'll put t as v minus u by a. So it turns out to be u into v minus u by a plus half into a into v minus u by a square. Okay, so if I solve it, I'll get my third equation of motion as v square is equal to u square plus 2as. So this is going to be my third equation of motion. Note that all these equation of motions have been derived keeping the acceleration of constant magnitude. Okay, so I have a constraint that the acceleration is of constant magnitude. Fine. So we stop here. We will continue with further discussion in the next video lecture. Thank you. Now let us begin off with few concepts related to projectile motion. Okay, so I'll begin off with brief concepts on projectile motion. Okay, so if I have a projectile which is fired from this point on the ground, okay, it will have some trajectory, right? So let's say this is my trajectory. Okay, and it has been projected with an initial angle of theta with an initial velocity of u. Okay, so the time of flight is denoted by t. It is given by 2u sine of theta by g. Okay, and the height, the maximum height, that is h, which this body attains during the projectile motion, is given by h is equal to u square sine square theta by 2g. Okay, and the range of the projectile, that is the horizontal distance which this particle has travelled from the initial point to the final point, is given by u square sine of 2 theta by g. Okay, so these are the three fundamental equations which we need to remember in projectile motion. Okay, now let us now deal with the case when the projectile is on an inclined plane. Fine. So on an inclined plane, let's say this is my inclined plane. Okay, and the angle of inclination of this inclined plane is theta. Okay, and the projectile is fired from this point. This is, let's say, the trajectory of the projectile, and the angle which the projectile initially makes with the inclined plane is, let's say, alpha, and u be the initial velocity with which the projectile was fired. Okay, so in this case the time of flight is going to be given by 2u sine of alpha upon g cos of theta. Okay, fine. So this is my time of flight of the projectile. This can easily be derived from the concept that I can divide the acceleration due to gravity into two components, g cos of theta and g sine of theta, and the initial velocity vectors into two components, and then I'll apply the equations of motions in order to get the time of flight. Okay, and the horizontal range, this range along the inclined plane for this projectile is going to be given by u square 2u square into sine of alpha into cos of alpha minus theta upon g cos of theta. Okay, so this is my range of the projectile along the inclined plane. Fine. Okay, and the third concept which I need to remember in case of projectile motion is the equation of trajectory. Okay, and that equation of trajectory I am going to write down for the simple projectile case, that is the projectile on the horizontal plane. So let's say at any point on the trajectory, its coordinate is x comma y, considering the initial point of projection as the origin. Okay, so the equation of trajectory is y equals x tan of theta minus half into g x square upon u square cos square theta. Okay, so this is my equation of trajectory. Fine. This can easily be obtained by replacing t equals x by u cos of theta, where theta is the initial angle of projection and u is the initial velocity of projection. Okay, in the expression, this needs to be replaced in the expression y equals u sine of theta into t minus half into g into t square. So basically in this particular expression I need to replace t by x by u cos theta, and I'll obtain this expression. Fine. So these are the three fundamental concepts which we need to remember in case of projectile motion. Fine. Now we shall begin off with few problems in kinematics. The first problem being this: 3 points are located at the vertices of an equilateral triangle whose side is A. They all start moving simultaneously with a velocity v constant in modulus, with the first point following the second point and the second point following the third point and the third point following the first point. How soon will the points converge? So in this problem I have an equilateral triangle. So this is my equilateral triangle. It has got side A. This is my first point, this is my second point, and this is my third point. The points move in such a way that the first point follows the second point, the second point follows the third point, and the third point follows the first point. Okay, and the particles, the points, move with a velocity of constant magnitude. The expected path is going to be something like this. The first point is going to move in this path, the second point is going to move in this path, and the third point is going to move in this path. Okay, they are going to move in nearly the same sense. Okay, the paths are going to be different, but the basis on which they move is going to be the same. Okay, so the expected curve is going to be similar. Okay, and they are going to be intersect at the centroid of the equilateral triangle. Okay, now in order to solve this problem, let us first consider the first point and the third point. We could have considered any of the three pairs Okay, but for timing, let us consider the first and the third point. Okay, now at any instant of time, by symmetry we can say that the 3 points are going to form an equilateral triangle. Now let's say at any instant of time, this first point is at this point, the second point is at this point, and the third point is at this point. Okay, they are definitely going to form an equilateral triangle. With the first point, even at this point, would follow the second point, this point, with a speed of v. The second point would follow the third point with a speed of v, and the third point would follow this first point with a speed of v. Okay, this is going to happen at any instant of time. They would always be forming an equilateral triangle. Okay, now we have considered the first point and the third point. Okay, let us find out the relative speed of the first point with respect to the third point. The first point initially is going to initially going to have a velocity of v towards the second point, and third point is going to have an initial velocity of v towards the first point. This angle is nothing else but 60 degrees. Okay, now the relative velocity of the first point with respect to the third point initially is going to be equal to, this velocity has some component along this direction, okay, which is going to be v cos of 60 degree, and this third point has some velocity v in this direction. Okay, so the velocity relative of 1 with respect to the third point is going to be equal to v plus v cos of 60 degree, that is 3v by 2. Okay, this was the initial relative velocity of particle 1 with respect to particle 3. We have observed that at any instant of time, these three particles are going to form an equilateral triangle. Even at this particular situation, the relative velocity of the first particle with respect to third particle would be equal to 3v by 2. Okay, and it would be directed in this direction. Okay, so basically we can say that the distance between the first and the third particle is decreasing at a constant rate. So we can write that if we say that at any instant of time the distance between the first particle and the third particle is s, so we can say that minus ds by dt is going to be equal to 3v by 2 minus ds by dt, because ds by dt is a decreasing number in this case. Okay, fine. Now if we integrate this, we'll get ds equals minus 3v by 2 into dt. If we integrate this, this should be from a to 0, because initially s was equal to a and finally s is equal to 0. That is when the points converge. When the points converge, s is equal to 0. Okay, and this should be from 0 to t, and we basically need to find out this value of t. Fine. So if we integrate it, we get 0 minus a equals minus 3v by 2 into t, which gives me t as 2a by 3v. So this is going to be the time which the particles are going to take to converge with each other. Okay, had we considered any other pair, we would have got the same answer. Fine. Now let us begin off with few problems in the topic of kinematics. The first problem being this: a ball starts falling with 0 initial velocity on a smooth inclined plane, forming an angle alpha with the horizontal. Having fallen the distance h, the ball rebounds elastically off the inclined plane. At what distance from the impact point will the ball rebound for the second time? So in this problem, I have an inclined plane which is something like this. It makes an angle of alpha with the horizontal. So this is the angle alpha, and I have a ball which was initially at rest and was at a height of h from the inclined plane. Now this ball starts falling downwards, it strikes the inclined plane with some velocity, let's say v, and then it rebounds elastically of the inclined plane and it follows, let's say, a path something like this. Okay, so basically I need to find out the distance from the impact point where the ball will rebound for the second time. So this is the point where the ball rebounds for the second time, and this is the point of the first impact. So basically I need to find out the distance between these 2 points, which is basically this distance. Okay, let's say it is s. Fine. Now let us first find out the velocity with which the ball strikes the inclined plane. Okay, that velocity can easily be derived from the law of conservation of mechanical energy. Initially, if I say that this is my reference point at this height, the ball will have only potential energy because it was initially at rest, and the potential energy would be nothing else but mgh. Okay, so mgh is going to be the initial total mechanical energy stored in the ball. Okay, fine. So this total energy is finally going to be converted into the kinetic energy of the ball as the ball reaches this point and strikes the inclined plane. Okay, with the velocity of v. Fine. So this energy gets converted into kinetic energy. So from where we get the velocity with which the ball strikes the inclined plane as root over 2gh. Okay, fine. So this is the velocity with which the ball strikes the inclined plane, and after striking the inclined plane for the first time, it rebounds elastically. Fine. Now this velocity with which the ball strikes the inclined plane has got 2 components. One component is going to be perpendicular to the inclined plane, and the other component is going to be parallel to the inclined plane. Fine. Now we can resolve this velocity into 2 components. The perpendicular component is definitely going to be v cos of alpha, and the parallel component is going to be v sin of alpha. I hope these things are pretty clear. Fine. Now by elastic collision, what we can say that the velocity perpendicular to the inclined plane is just going to reverse after the collision. Okay, the velocity parallel to the inclined plane is not going to reverse after the collision. Okay, the velocity parallel to the inclined plane is going to remain the same after the collision. Fine. So after the collision, the state of the velocity would be something like this. The perpendicular component of the velocity after the collision would be v cos of alpha in this direction, and the parallel component would be v sin of alpha. Okay, now this is going to be the state of the ball just after the collision with the inclined plane. Okay, fine. Now gravity is the only acceleration which is acting on the ball. Okay, so gravity is going to be vertically downwards. Its magnitude is going to be g. Okay, now this gravity also has got 2 components. One is perpendicular to the inclined plane and one is parallel to the inclined plane. Okay, so if I divide the gravity into 2 components, the perpendicular component is going to be g cos of alpha, and the parallel component is going to be g sin of alpha. Now these 2 things are worth considering while we solve the problem. Okay, now we can write down separate equations of motion along 2 perpendicular directions. Okay, the first direction is going to be perpendicular to the inclined plane, the second direction is going to be parallel to the inclined plane. Okay, fine. Now if I write down the second equation of motion perpendicular to the inclined plane, what I can say is that perpendicular to the inclined plane, the net displacement between the 2 impact points is going to be equal to 0. What I want to say is that along this direction, the ball did not have any displacement while it moved in this particular trajectory. Okay, fine. So the net displacement in the perpendicular direction is going to be 0. If I say that this whole equation is being written taking this as my positive direction, so gravity the component of gravity has to be written negative in this direction. Okay, so this 0 would be equal to ut plus half at square, right? So u is v cos of alpha, which would be written positive because it is in this direction, right? Fine. V cos of alpha t plus half into, I'll write minus g cos of alpha, right? Into t square. Okay, so I get 1t cancelled, I get cos of alpha cancelled, from where I get t as 2v by g. So this is the time of flight between the two collision points. Okay, now I can write down the second equation of motion in the direction parallel to the inclined plane, right? Parallel to the inclined plane, the displacement is going to be s. Okay, so I'll write down s as v sine of alpha v sine of alpha into t plus half into g sine of alpha into t square. Okay, fine. This whole equation has been written taking this as my positive direction. Okay, now s can be written as v sine of alpha into t can be written as 2v by g plus half into g sine of alpha into 4v square by g square. Okay, which implies s can be written as 2v square sine of alpha by g plus 2v square sine of alpha by g, which can be written as 4v square sine of alpha by g. Now I know that v is equal to root 2gh, right? So v square is going to be nothing else but 2gh. Okay, so s turns out to be, if I put in v square as 2gh, 4 into 2gh into sine of alpha by g, I get g cancelled. So this gives me s as 8h sine of alpha. So therefore s turns out to be 8h sine of alpha. So this is going to be the distance between the two impact points. Fine. Let us now move on to the next problem, which is this. Okay, a particle moves in the plane xy with horizontal velocity v equals ai cap plus bx j cap, where I and j are unit vectors of the x and y axis, and a and b are constants. At the initial moment of time, the particle was located at the point x equals y equals 0. Find the equation of the particle's trajectory yx. Okay, fine. So in this problem I have been given that the velocity of the particle follows the equation ai cap plus bx j cap. Velocity can basically be written as dx by dt I cap plus dy by dt j cap. Okay, this is because v equals ds by dt, where s is the displacement vector and displacement can be written as x plus xi plus yj. Okay, so if I differentiate this, I'll get this equation. Okay, fine. Now these two equations can be compared, right? So I can write dx by dt I cap plus dy by dt j cap must be equal to ai cap plus bx j cap. Okay, now the coefficients of the individual directions are going to be the same, right? So I'll write down, this equation implies dx by dt must be equal to a, which implies x equals at plus c, right? Now I know that at the initial point the particle was located at x equals 0, so this would imply c equals 0, so I can write x as at. Okay, now if I compare the coefficient of j cap, I'll get dy by dt equals bx, right? Now if I put in x equals 80, I'll get, which would imply dy by dt equals b into x can be written as 80, right? So this can be written as dy equals b 80 into dt. If I integrate on both the sides, I'll get y as b at square by 2 plus c. Okay, now I know that at t equals 0, y is equal to 0. If I put in this condition, I'll get c as 0, that is the constant of integration as 0, which gives me y as ba t square by 2. Now I can put t as x by a, right? So if I put in t as x by a, I'll get y as ba into ba by 2 into x by a whole square, which gives me y as b x square by 2a. So this is going to be the equation of the particle's trajectory in terms of y and x. Fine. Now let us begin off with the next problem in the topic of kinematics, which is this. A point moves an arc of circle of radius r. Its velocity depends upon the distance covered s as v equals a root s, where a is a constant. Find the angle alpha between the vector of the total acceleration and the vector of velocity as a function of s. Fine. So in this problem I have a point which is moving in a circular arc, which is something like this. Okay, its radius is r. Fine. So this point is moving in such a way that the velocity is given by this, where s is the distance which the point has traveled. Okay, so I basically need to find out the angle alpha between the vector of the total acceleration and the vector of velocity as a function of s. Fine. So actually, while the particle moves in a circular path it will have two accelerations. One would be tangential acceleration, which would have the same direction as that of the velocity vector, and one would be radial acceleration, which would be radially directed inwards towards the center of the circle, and it would be perpendicular to the velocity vector. Okay, so the tangential acceleration is basically given by dv by dt. Okay, and this can also be written as dv upon ds into ds by dt. Okay, this can be written as v dv by ds. Okay, fine. So from this expression I can find out dv by ds as dv by ds is going to be a by 2 root s. Okay, so if I put in this value in this expression, and if I put in the value of v as a root s, I will get at as a root s into a by 2 root s, which gives me at as a square by 2. Fine. Now this at is going to be directed towards the velocity vector. Fine. And the ar is going to be directed radially towards the center of the circle. Fine. Now ar is given by ar is going to be nothing else but v square by r. Fine. So v square can be written as a square s by r. So this is my magnitude of ar. Fine. Now, and this is the magnitude of at. Fine. So now my diagram is going to be something like this. at, this is going to be ar, and this is going to be my net acceleration. Fine. Fine. And this is also going to be the direction of the velocity vector at any instance of time after it has traveled a distance of s. Fine. I basically need to find out the angle alpha between the vector of the total acceleration and the vector of velocity, which implies I basically need to find out this angle, which is also the angle between the tangential acceleration and the net acceleration. Fine. So if I move this particular vector parallelly, I can move it here. Okay, so tan of alpha now can be written as ar by at. Okay, so if I put in the value of ar as a square s by r and at as a square by 2, this expression turns out to be 2s by r. Fine. So this gives me the angle alpha as tan inverse 2s by r. So this is going to be the expression of the angle between the total acceleration and the vector of velocity as a function of s. Fine. I need to find out the total, the tangential and the normal accelerations of the balloon. Fine. So I have got the total acceleration as v naught into a along the x-axis. Fine. So the tangential acceleration of the balloon is going to be directed along this direction, let's say. Okay, and it would be parallel to the actual velocity, net velocity vector of the balloon. Fine. So this is basically going to be parallel to the v net. Okay, now let us find out the direction of v net. Fine. Along the horizontal direction, Vx is nothing else but a into y, and along the vertical direction Vy is nothing else but v naught, and this is the net velocity vector. Okay, fine. the same is going to be the direction of the tangential acceleration, and perpendicular to it would be the normal acceleration, and the actual acceleration is directed along the x-axis, whose magnitude is given by v0 into a. Fine. So basically v0 into a, that is the net acceleration, is going to have two components, one normal component and one tangential component. Okay, and this angle is basically going to be alpha. Fine. So basically AT is nothing else but the net acceleration into cos of alpha, that is v0 into a into cos of alpha. Okay, so this would turn out to be v0 into a into cos of alpha is ay upon root over ay square plus v0 square. Okay, so this is basically going to be my tangential acceleration. If I simplify it, I'll get AT as a square into y upon root over 1 plus ay upon v0 square. Okay, and the normal acceleration is going to be nothing else but v0 into a into sine of alpha. Okay, so this can be written as v0 into v0 into a into sine of alpha is nothing else but v0 upon root over v0 square plus ay square. Okay, so this turns out to be a v0 square upon root over v0 square plus ay square. Okay, so this is the normal acceleration. Fine, this is what we had to find out in the second half of the problem. Fine, let us now move on to the next problem in the topic of kinematics, which is this: a cannon and a target are 5.10 kilometers apart and located at the same level. How soon will the shell launched with initial velocity of 240 meters per second reach the target in the absence of air drag? So in this problem I have no air drag. Okay, and I have a cannon and a target point which are at the same level. Fine, so let's say this is my cannon and this is my target point and they are at the same level. Fine, now I have said that the distance between the cannon and the target is 5.10 kilometers. This can also be written as 5100 meters, right? And the shell is launched from the cannon with an initial velocity of 240 meters per second such that it hits the target. Fine, so let's say that it is going to follow a parabolic path, something like this. Fine, we have got no information about the angle with which the shell was projected, and the shell was projected with an initial velocity of 240 meters per second. Fine, so let us now see how we approach with the problem. Fine, now I know that the range of projectile is given by u square sine of 2 theta by g. Okay, so this is the range of the projectile. This range is going to be equal to the distance between the cannon and the target, right, which has been given to me as 5100 meters. Fine, I know the value of u, I know the value of g, right? So if I put in those values in this equation, I'll get 5100 equals u square, that is 240 square into sine of 2 theta by, if I take the value of g as 9.8. Fine, so from here I get sine of 2 theta as 0.8677. Fine, this is nearly equal to root 3 by 2. Okay, fine, so I can say that theta, twice of theta, is nearly going to be equal to 60 degree, which implies theta is nearly going to be equal to 30 degrees. Okay, now I know that the time of flight is given by 2u sine theta by g. Okay, so time of flight is given by 2u sine of theta by g. Okay, and that is something which I need to find out. I need to find the time which the shell takes to reach the target in absence of air drag. Okay, all these equations have been written considering that there is no air drag. Okay, that is the ideal situation of projectile motion. Fine, so I know that theta value is 30 degree. So if I put in the value of sine theta in this expression, I know the value of u, I know the value of g, I'll get the value of t. Fine, so this implies t equals 2 into 240 into half, and g's value can in this case be taken as 10, or either it could be taken as 9.8. The answer would nearly be the same. Okay, so this gives me the time of flight as 24 seconds nearly. Fine, so this is going to be the time which the shell is going to take to reach the target. Okay, let us now move on to the next problem in the topic of kinematics, which is this: a solid body rotates about a stationary axis so that its angular velocity depends on the rotation angle phi as omega equals omega naught minus a phi, where omega naught and a are positive constants. At the moment t equals 0 and the angle phi equals 0, find the time dependence of the rotation angle and the angular velocity. Fine, so in this case the angular velocity is basically given by omega. Okay, fine, so I have been given that omega is equal to omega naught minus a phi, where omega naught and a are positive constants. I have been given the condition that at t equals 0, phi is equal to 0, that is the rotation angle was equal to 0 at t equals 0. Fine, now omega is given by d phi by dt, right, that is the rate of change of the angular displacement, right? So omega can be written as d phi by dt, which turns out to be omega naught minus a phi. Basically I need to find out the expression of phi as a function of time. Fine, basically I need to find the time dependence of the rotation angle. Fine, so this can further be written as d phi by dt plus a phi equals omega naught. Fine, so this is a linear differential equation, right, in which the integrating factor is e to the power a t. Okay, the integrating factor is is e to the power at. Okay, so the solution of this linear differential equation becomes phi into pi into e to the power at equals integral of omega naught into e to the power at. Okay, so this can also be written as omega naught into e to the power at by a. Okay, this is E. Okay, sorry. This is E. Fine. Omega naught into e to the power at upon a. Fine. Plus c. We will also have a constant of integration. Fine. So this, if properly written, would turn out to be phi into e to the power at equals omega naught into e to the power at by a plus c. Okay, now I have been given that at t equals 0, omega naught equals, at t equals 0, phi equals 0. Okay, at t equals 0, phi was equal to 0. Fine. So if I put in this condition, I'll get c as minus omega naught by a. Okay, so that gives me this expression as phi into e to the power at equals omega naught by a into e to the power at minus 1, which gives me the angular displacement as phi as omega naught by a into 1 minus e to the power minus at. So this is the expression of the angular displacement as a function of time. So I know the expression of angular displacement as a function of time, and I have been given that the angular velocity is omega naught minus a phi. So basically, in order to find out the expression of angular velocity as a function of time, I need to replace phi as this expression here. Okay, so that would give me omega as omega naught minus a into phi can be written as omega naught by a into 1 minus e to the power minus a t. Okay, so a gets cancelled, which gives me omega as omega naught into e to the power minus a t. Okay, so this is going to be the expression of the angular velocity as a function of time. Fine. Now let us begin off with the next problem in the topic of kinematics, which is this. Okay, so a balloon starts rising from the surface of the earth. The ascension rate is constant and equal to v0. Due to the wind, the balloon gathers the horizontal velocity component vx equals ay, where a is a constant and y is the height of ascent. Find how the following quantities depend on the height of ascent. The horizontal drift of the balloon, which is represented as xy, the total tangential and normal accelerations of the balloon. Fine. So in this problem, I have a balloon which started rising from the surface of the earth and whose ascension rate is constant, which implies that it moves upward with a constant velocity that is given by v0. Fine. and I have been given that its velocity along the x direction is a function of its ascent. Okay, that is a into y, where y is the ascent. Okay, so y is basically the vertical distance which the balloon travels. Okay, so y can be given by v naught into t. Okay, and vx is nothing else but dx by dt. Okay, this is vx, and this has been given to me as a into y, and y can be replaced by v naught into t. So I get this equation as v naught into a into t. Okay, so this is basically my dx by dt. So from here I get dx as v naught into a into t dt. So if I integrate on both the sides, I'll get the expression of x as v naught into a into t square by 2. Okay, now from this particular expression I can replace t by v naught by y, which will give me the expression of x as v naught which will give me the expression of x as a by 2 v naught into y square. This is basically the expression which we had to find out. Okay, fine. Now let us move on to the next subpart of the question, which asks me to find out the total tangential and normal accelerations of the balloon. Fine. So from this expression I can say that the acceleration along the x-axis is going to be the double derivative of x with respect to time. Okay, sorry, it would be d square x upon dt2. Okay, so this is nothing else but v naught into a. Okay, so this implies that the balloon is having a constant acceleration along the x-axis whose magnitude is v naught into a. Along the y-axis the balloon is not going to have any acceleration. Okay, because it is moving with a constant velocity along the y-axis. Okay, so this is basically the direction of the net acceleration of the balloon. Fine, I need to find out